in this module, I want to go over how to describe state machines in Verilog. Okay, so here let's start with from the top. So we have a module that we're going to call simple. It's several variables: clock, reset, W, and out. So we're going to say that the clock, reset, and W are inputs to the system, and out is an output. Also, we're going to say that there are two registers, so essentially internal variables that change during the simulation or during the operation. The first one is called present state, PS, and the second one is called next state, NS. This notation, which you've probably already seen, implies that there's actually sort of that is a 2-bit vector. So basically there's two components to present state 0 and present state 1, each of which you could call individually and talk to individually. So what this specifies at the highest level is already essentially the following diagram. So we don't know anything about the combinational circuit. We just know that there will be some. But we already said that, okay, there's two states essentially in this state machine. So we will have two flip-flops. I mean, that's just determined by the size of these vectors PS and NS. I can draw this like that. Q and D, Q and D. Both of these flip-flops are obviously hooked up to a clock. Okay. And then what's coming into the system here is the next state, and what's held on the flip-flop is the present state. Okay, and I'm going to use this notation here, 2, so this slash here through the line basically implies that there's actually 2 wires here. I'm just too lazy to draw them, and this will become a convenient notation once you have systems with many more wires involved. Okay, so this line with a slash through and the number 2 or 2NS next to it here implies there's really 2 wires that come out of here. Then in addition to this, what I've drawn here, there's essentially 2 more things that are specified just that are obvious just from the description above. One is that there is an input W that sort of goes into the combinational circuit, and there's an output called out. Okay, so just from this sort of header of this function simple, you can understand several things about the state machine that we're going to build. Okay, so the thing that wasn't specified on that previous slide is essentially the combinational logic part, and this is what this code here does. So at the top here we have this line that says parameter 10, a equals 2-b00, etc. So this line essentially provides the state encodings. Right, so basically this state machine has 3 states, and we're going to say that state A is going to be encoded as 2'B00, which means this is a 2', it's the 2-bit binary number 00. And similarly, B, the encoding is the 2-bit binary number 01, and C is 10. Okay, so there are 3 states, and that's the encodings that we're going to use. Then we're switching to the next state logic, and I think this is actually very intuitive to read. So we have an always at star statement, which just means it's a combinational logic system, meaning that at star again is sort of says that the values will be updated every time an input to the system changes. And we're going to introduce this case statement, which basically we can interpret as the case for the present state. Okay, so if we're in case A, which is 00, if the input W is true, then next state is B. So I can just start drawing that. So I have a state A here, and I have a state B here, and I have a state C here with the encoding 0, 0, 0, 1, and 1, 0. And I said if W is true and I'm in A, I go to B. So worry about the output a little later. Else, I'm going to stay in A. Okay. Now, if I'm in state B and W is true, then I'm going to C. On the other hand, if W is not true, so else, I'm going back to A. Finally, if I'm in C and W is true, then I'm staying here. And else, I'm going to A. Okay, so just from this code, it's very intuitive how you can derive the state diagram for the system. This part here is important and it's necessary. They really need this. It's basically saying that adding the x's to your eventual state table, right? So this is saying this state machine only has 3 states. So there could be a state 1, 1, but we don't need it. So we just have to say that in that case, we don't care what happens, but if for whatever reason you end up in a state 1, 1, you basically have to help the machine to get out of it again. And that's what this code does. Okay, so that's basically just filling in the x's in your state diagram that allows you to find the minimal version of the machine that you want to build that sort of will behave correctly. Now the output logic I haven't written down yet. It basically says, I've written it in this way, I'm going to say here, I'm assigning the output to be essentially the value of the C state. So basically, I'm going to say that the output is false, except if I was in state C. So here, this is a 1, this is a 0, 0, 0, 1, 0. So again, so remember in these state machines, I always have to associate an output with an input. And you could have done this differently. You could have written down, an independent sort of always at star block for the output, going through all the cases, or you could have written the output into the next state logic block that I have up here. So there's different ways of doing that, but this is one way that sort of correctly specifies the system that I want. Okay, so then of course, I also explicitly need to introduce the flip-flops. And as we've seen previously, right, this is actually very simple in terms of Verilog. So I'm just going to say that there is an always at pos edge clock block. And I'm going to say if reset is true, present state or is A, else present state at the clock edge becomes next state. Or the other way around. Next state at the clock edge. So the value that's computed in the combinational circuit at the clock edge is read into the present state, the value that's held within the flip-flop. Okay, so all of that this really does is just to specify these two flip-flops here. And again, it's two flip-flops because of the size of the system that was defined 2 slides ago. There's an NS1, present state 1, so 1 flip-flop here, and then the other one here. Okay, so now we've essentially defined this complete state machine. And I think this is all fairly intuitive. the next thing I want to do is also quickly walk you through how to write a test bench for a state machine. So this module here is called simple test bench. Clock, reset, and W here are registers because they change during the simulation. Out is a wire. Then simple is the device under test. That's the state machine we just defined on the last 3 slides. We're going to use a clock. We're going to set the clock period, which is a parameter, to 100. We're going to initialize the clock at 1, the high value, and we will toggle the clock at every 50 time units. Okay, so this is fairly straightforward. Okay, so then we're going to sort of run or specify a sort of diagnostic series of inputs, and we want to see that our system behaves the way we expect it to behave in response to this series of inputs. So again, positive edge clock here. That would be time values just for simplicity. This is, or for convenience later, this is 100, 200, 300, 400, 500, etc. Right? Every positive edge clock, that's another 100 time units. So I'm going to say I'm going to wait to that first positive edge of the clock here, and then I'm going to switch reset to 1, wait for the next edge, set reset back to 0, set W to 0, wait to the next edge, don't do anything, wait another full clock period, and a third one, and a fourth one, and then only switch W to 1, wait another clock period, switch W back to 0, switch it back to 1, wait 3 clock periods, switch W to 0, wait another clock period, and end the simulation. Okay? This is fairly straightforward. So this is, you've essentially seen this kind of, or used this kind of stimulus patterns before in different contexts. And this is just meant to try a few different combinations and just see that everything works the way you want it to. And on this slide, I've essentially just drawn what this should generate, right? So we set the clock starts high, and it just gets toggled every 50 time units. We set that the reset gets switched to 1. That's the first thing that happens after 100 time units, and before that, we actually don't know what reset would have been. So it goes up and then down again and stays low. Similarly, the first time we do anything to W, to the input, was at here after 200 time units. Before that, it was undefined, and then there was sort of a series of changes to W. I mean, you can take the code from the previous slide and convince yourself that you get the same drawing. This here is a bit trickier, so that's the present state value. So if you remember your state machine, right, what it essentially says that if you're, this is actually shown at the bottom of the slide here. So here it says, in the beginning, of course, we don't know what state we're in. Then we hit this reset. Reset is true, so at this clock edge, at 200, because reset's been true for a whole clock edge, I now know, because the reset is attached here to state 0, that I'm going to be in state 0. Then nothing happens up to here, and because if you're in state A and W is true, you're going to state B. So once W was true for a whole period here, so at this next positive edge, you're looking at the fact that W is true here, you're in state A, and so you're switching to state B. Similarly, if you're in state B, but the input is low, you're actually going back to A, that's the 0, 0. Now the input is high, or has been high for 1 clock cycle. You've been in state A for 1 clock cycle, so you're going back to B. Now in this case, if you're in B, but the input is actually true, well then you're going to C, and you're going to stay in C up to the point where the input has been low for 1 clock cycle, so that's the value that's being held. You've been in this state 1, 0, C, and now because you're in 1, 0 and you see input is low, you're actually going back to A and you're ending the simulation, right? Similarly for the output, I actually haven't drawn that yet, but you can convince yourself that this should look something like this, where again in the beginning we don't know what the value is. Then actually the output's going to be low all the way to here, and only then does it go up, stay high, and down again. Okay, you can convince yourself that it's true, and of course when you're writing these test benches yourself, I mean, it's helpful to kind of choose the combinations of inputs and say it's in such a way that you're kind of going through all possible states and checking all possible combinations of inputs to kind of really see that you get what you're expecting to get.